AP Calculus AB, Unit 6, Day 13 lesson. This possibly is on the back of the 612 note sheet. So we're going to talk about inverse functions and their derivatives. So this applies to any functions with inverses. So we'll go over some of the basics about inverses that you should have learned in previous math courses, probably going back to Algebra 2. And I'll just kind of draw some generic curves to start with. Let's say, we'll start with something that looks kind of exponential. I mean, there's a famous pair of inverse functions that we deal with a lot lately, exponentials and logs. But, we're just saying this is the original function. And so it gets reflected across y equals x. So it looks something like this. All right, so it gets reflected over here across y equals x. So this would be the inverse function, which we often label with a superscript -1, not to be confused with power. Okay, so some people think oh, that's a -1, and that must mean it's the reciprocal. Nope. Okay. Anyways, there's some basic things. If there's a point on this graph with x coordinate A and y coordinate B, that gets translated over to the other graph where there's a corresponding point with the y variable becomes the x and the x becomes the y. So anything that's x becomes y, anything that's y becomes x. We specifically want to start talking about the slopes, the derivatives of these, and how they relate together. So we haven't really talked about that before. So if we were to draw like a slope here, or a tangent line, maybe it looks something like that. All right, so this is a tangent line, and the slope of this would be the derivative. Now over here on the corresponding one, if you were to draw the tangent line, if you were to do this just right, what would happen is they would cross each other, always cross each other on y equals x. Any pair of corresponding tangent lines will cross each other on y equals x. So it's kind of an interesting result. So this is the tangent line of the inverse, which will give you the derivative of the inverse. So there's some kind of relationship. Now, they're not parallel, obviously, they intersect. Maybe there's one pair that end up being parallel. They're not perpendicular. These don't look like a right angle, even though there's probably one pair that might be perpendicular, but in general, they're not. But what will happen, I'll give you some values. So for instance, let's say if the slope here was 5, the slope here would be 1/5, okay? What happens is if you multiply them together, you're always going to get 1. So they're actually the reciprocal of each other. They always intersect on y equals x. Okay. If AB is on fx, then BA is on the inverse. Those are some of the basic things. But the big thing we're getting at is the slopes. What happens is the slope of the derivative of one is always going to be the reciprocal of the slope on the other one. So you could go either way. You could say now you got to be careful here. So the derivative of the inverse, if you flip it upside down, in this case, like, if the slope here is 5, then, or the slope of this one's 1/5, then you're going to flip it upside down and you're going to get 5. So the slopes, the derivatives are reciprocals. Now, this actually totally makes sense. It's not even that complicated. The slope of this is going to be rise over run. It's going to be change in y over change in x. But remember, the y's on this become the x's on this, and the x's on this become the y's on this. So the rise over run, the change in y over change in x, the rise ends up in the bottom over here. Rise over run becomes run over rise. Because the whole thing, that everything that's x becomes y. So the change in y here is going to be the change in x here. And the change in x here is going to be the change in y here. And so the slope is going to be the same, but it's just going to get flipped upside down. So that's the main thing. So I'm gonna show you some different ways that we could use or not use this information. We really do want to use this little fact as much as we can. But let's look at a couple problems and look at a couple different ways to do it. And I'll try and convince you. So find the slope of the inverse function. Now, one of the things you got to watch out here is that the slope of one is at the x value here corresponds to the slope of the other one at the x value here. So what you plug in a 1 is going to be different than the other one. Right? F prime of A is the same as f, the inverse of f at B prime. Okay, I'll try and point that out. Now, let's draw a picture for these first couple ones. So this is a parabola. And so, looks like that. Generic quick parabola. Goes through 0, 0. So that's that. And then so the inverse function of a parabola would look like this, flipped sideways. Like a sideways parabola. So that's one of the things that happens is the inverse of a function always looks like a sideways version of it. Now there's this little extra thing right here that says x has to be greater than 0. So that means on the original graph, we are only dealing with the right half of it. And there's a really good reason for that, because when we flip this is no longer a function. It doesn't pass a vertical line test. But if we start with only the right half of the parabola, then the flip version is just the top half. So now it is a function. So we could start with the left half of the parabola or the right half and get the inverse function. But if we take both right and left half, we get something that's not a function. So that's a good reason why they're giving us that issue here. Now, let's say like we want, this is the original function, right? And this is the inverse function. So we want the slope of the inverse at x equals 4, which would be like, something like that. And so if we could find the slope in the other guy and just flip it upside down, that'd be the easiest. The thing is, it doesn't match up to 4. So the reason that we want to use this, where we just flip it over, is because finding the derivative of this function, or the original function, is super easy. And if we plug 4 in, this is what some people might think we're going to do. Plug 4 in, we get 8. And then so we think the answer is 1/8, which we see right here. But that is not correct. Okay? So 4, since 4 is the x value for this guy, it's going to end up being the y value for the other one. So we're going to have to somehow figure out what the correct x is. So 4 is the y value for the inverse, or for the original graph, because we're x equals 4 is on the inverse. So let me show you two different ways of doing this problem. That's all just kind of extra stuff to get you thinking. So I'm going to have two approaches. I'm going to call one old school approach and one new school approach. So the old school approach is sort of like, don't use this new information I taught you today. Take the original function, maybe write it as y, and find its inverse. Just find the inverse like you learned how to do in algebra 2. Swap the x's and y's, right? Solve for the new y, square root of both sides, plus or minus. Now, is it the plus or the minus? Well, x had to be positive for the original function, which anything that's x becomes y. So the domain of the original function becomes the range of the inverse. So that means y has to be greater than or equal to 0. So we're going with the positive because of that. And so we're getting, so that's the inverse function, just the positive, okay, because of this. Now, let's find the derivative of that. So if you want to find the derivative of the inverse function, we can do that. You got to get the inverse function first. So this is the same thing as x to the 1/2. It's going to be 1/2 x to the negative 1/2, right? And so then we can go ahead and just plug 4 into this. And we'll get 1 over 2 square root of 4 is 1/4. So the answer is 1/4. So that's an old school approach. That sort of, we didn't use that new fact today that said that the slopes were just the reciprocals of each other. We went and brute force, found the inverse function, found its derivative, plugged x equals 4 in. The problem with that is it's a lot of extra work. And sometimes it's going to be super hard to get the inverse function or impossible. So you're going to want to use the new school approach as much as you can, okay? So the new school approach says, you know what? Let's just find the derivative of the original function, plug the number in there, flip it, be done, okay? The problem is if x equals 4 on the inverse function, because that we're trying to find the slope of the inverse function x equals 4. So x equals 4 is for the inverse function. That means y equals 4 on the original function, right? And we got to find the right x value to plug into the original function derivative. It's not 4, okay? So if we know the y value, though, this is something you guys learned a long time ago in math. If you know the y value, you should be able to find the x, okay? So if y equals 4, plug it into the original function and solve. Plus or minus, so x equals plus or minus 2 gives you y equals 4. We're going to go with the positive because they said x is supposed to be positive. This is the x value on the original function that we want to plug into the original function's derivative. So we're going to plug 2 in. So that's the derivative of the original function. So the derivative of the inverse at 4 is going to be that flipped upside down. And we get the same answer. We get 1/4. But it's a little tricky, okay? So let's do another one. We could do, let's just start with the new school approach, okay? So the answer, by the way, here was 1/4, okay? Don't plug the x equals 4 into the original function. So here, find the slope of the inverse at x equals 6. So x equals 6 is on the inverse function, right? Which means that y equals 6 is on the original function, right? What's x on one becomes y on the other, which means we could then find what x value is on the original function. So this one's a little more complicated than the other one. I would factor, unless you really like quadratic formula. So we get those answers. Now, again, they said x had to be greater than 0, so we're going to go with this one and not that one. Okay? And so now we're going to take the derivative of the original function, which is super easy to do, 2x minus 1. And then we're going to plug 3 into it. Which is going to give you 5, which means that the inverse at x equals 6 derivative is going to be that flipped upside down. Okay? That's the new school approach. Now, let me show you the old school, and you'll start to realize that you want to avoid old school. A lot of times you're just not going to be able to do it. So old school approach says, you know what, let's ignore this new cool fact that the slopes are just upside down. Let's just find the inverse function, like we learned how to in Algebra 2, and then take its derivative using our derivative rules, and then plug x equals 6 into it. It's a lot more work though. So the first thing we got to do is we got to find the inverse function. So we are going to swap the x's and the y's. And then you got to solve for y in terms of x. This one's a little harder than the last one. It's not nearly as hard as it could be. To solve for y here, you have to complete the square, which I feel like is like a bad word for you guys in math, even though you really should learn how to do it in like Algebra 1. So completing the square is you want to get a perfect binomial squared over here. And the way you do that is you try and pick the just perfect number to add here. And the perfect number is always the middle number divided by 2 squared. And we can add anything new we want as long as we balance it out by doing the other side. So we essentially added a positive 1/4 here. We need to add a positive 1/4 over here. So now the function looks like this. And now you can complete the square. Y minus 1/2 squared. And this allows you to now solve for y. Square root of both sides, plus or minus. We're going to go with the positives because if x is greater than 0 on the original function, then y has to be greater than 0 on the inverse function. And solve for y. So we get y equals square root of x plus 1/4 plus 1/2. So this is the inverse function. So that was all work just to find the inverse function. Now we totally avoided over here. Now we got to take the derivative of this guy, which is much messier than just taking the derivative of the original function. The original was super easy, powerful. This one's going to be rational exponents, 1/2, x plus 1/4 to negative 1/2. Probably want to rewrite it. 1/2 square root of x plus 1/4. And now you can plug x equals 6 into it. And it's going to be 1/2 6 plus 1/4. Probably want to clean this up, give the least common denominator. And it's going to be 1/2 square root of 25/4, which is going to be 1/2 times 5/2. The 2's are going to cancel, and eventually you get 1/5. Okay? That's way more work and way messier work. And honestly, it wasn't even that bad. You're going to get ones that you can't solve for y if you try and find the inverse. So you're stuck. Okay? Now, the other option, there is sort of a new / old school hybrid approach, but I would just go with the whole new school thing. The new old school is to find the inverse function, but don't solve for y, use implicit differentiation. And so you would say, okay, well, derivative of x is 1 equals 2y dy dx minus dy dx. So implicit differentiation, and you can't get y by itself. And there's your slope, but you would need the y value. And we know the x value is 6. So you'd have to figure out what the y value is on the inverse. And the best way to do that is to say, well, if x equals 6 on the inverse, then y equals 6 on the original function. And so then we could solve for x on the original function. And then we know it's going to be the positive, which means that y equals 3 on the inverse, which means that's what you're going to plug in up here. 1 equals 2 times 3 dy dx minus dy dx. So we get 6 dy dx is minus 1 dy dx is 5 dy dx is equals 1. And you solve for dy dx, and you get 1/5. But let's really try and go with this new school approach, okay, as much as we can. Maybe we could do one more problem on today's assignment. So today's assignment's a worksheet. So let's look at one of these. Let's look at number 4. Okay, let's try and do this new school approach. Find the slope of the inverse at x equals 8. So one of the first things I want to do is say, well, if x equals 8 is on the inverse, then that means y equals 8 is on the original function, right? But we got to find the x value that goes there. So we could set y equal to 8, x cubed, cube root of both sides, no plus or minus is odd root, x equals 2 on the original function. So we got to clear that up. And then take the derivative, which is really easy. Okay, so this is avoiding finding the inverse function, which is its own mess. This is avoiding finding the derivative of the ugly answer you get for the inverse, taking the derivative, this super easy one. The thing you got to do, though, is make sure you plug in the correct x. We want the slope of the inverse of f at x equals 8, but that's on the inverse. That corresponds to x equals 2 on the original function. So we got to plug that one in. So then that means the inverse function at x equals 8's derivative is 1/12. That's the new school approach. It's way easier. It's way cleaner. Take advantage of it. So try the rest of today's assignment. There's a little bit extra practice on the back. Derivatives of logs and exponentials. Just to give you a few more to try. So that's it.